Well, a scalar multiple of vector is just an adjustment of its length and possibly its direction if the scalar is a negative number. See, if this is vector u, then this one, I tried to draw it twice as long as this one, but notice it's pointing in the same direction, and of course a half a u would only be half the size of this, right? But still pointing in the same direction. What I drew here was negative u, and if you can tell, it's the same vector as vector u, only pointing in the opposite direction. Negative 2u would just have the arrowhead down here. So here's some properties of vector operations. Call this theorem 11.1. U plus v equals v plus u, and the fancy word for this, if you don't know it, is, maybe you can fill it in. Vector addition starts with a C, commutative. Vector u plus v then added to vector w is the same as vector u plus the sum of v and w, and the word for that is associative. It's real easy to prove these. All you have to do is let u be u1 plus u2, or sorry, u in component form u1, u2, v be v1, v2, and then write them either way. Same thing, and let w be w1, w2, and then write all the possible ways of that. It's a pretty straightforward thing to prove. I won't even waste your time with it because they are straightforward. And vector u plus the zero vector is vector u. Vector u plus vector negative u is the zero vector. In other words, if I added this one to this one, I'd get the zero vector. They sort of cancel each other out. How about this interesting one? Scalar a times scalar b times u is the same as scalar a times scalar b times vector u. You probably would expect that. Here's an interesting one. Commutative, can we say that scalar multiplication distributes over scalar addition? That's kind of weird. But vector a plus b, scalar a plus b times vector u is the same as scalar of a plus the scalar of a times u plus the scalar of b times u. And scalar a times vector u plus v is scalar a times vector u plus scalar a times vector v. You would expect that. 1 times vector u is u, and 0 times vector u is the zero vector. That's a little touchy there because remember, this is a scalar, this is a vector. This is a scalar, this is a zero scalar, but this is the zero vector. Component form would be 0, 0. So if I was teaching you in class, I'd say pick one of these and prove it and share it with a neighbor. But since this is online, you should be able to just pick one and prove it without too much difficulty. So yeah, if you just start out letting u be vector u1, comma u2, and v be v1, v2, then it's really easy to prove this one because you can just write it in the opposite order. And since addition is commutative, then so is vector addition. So the length of a scalar multiple. Here's another theorem. Let v be a vector, a be a scalar. Then the length of a times v. You want to make a good guess? Well, of course. It's a times the length of v. The length of this vector is twice the length of this one. Duh. And again, that's another easy proof. You know, I probably could have typed this one in a nicer way by saying, instead of saying, then the length of AV, wow, I could have done this with symbols. I could have said, let me see if I can manage to get through this. I could have said, the length, no, you know why I can't do this? Because my V here, or my A doesn't look like a scalar. Rats. Didn't think about that when I started typing this. Well, guess I should have, but anyway, it would be A, the scalar, times the length of vector v. And that would be very likely guess, right? In other words, the length of this 2 times vector u is twice the length of vector u. Duh. So we could easily prove this. Just let vector v be v1, v2, and multiply it, do a scalar multiple a times it, and then check the length of this vector, square root of v1 squared plus v2 squared, multiply that by a. When you do that, this is going to be the square root of a v1 quantity squared, so a squared v1 squared plus a squared v2 squared, and then the square root of a squared factors out, so a factors out, so it'd be an easy proof. Okay, so I talked about how to prove this. I didn't do it, but it would be an easy one. So what is a unit vector? You could probably guess this one. A unit vector is a vector whose length is 1. So given a vector v, how can we find a unit vector that points in the same direction of v? And that's going to be something that's useful. So given a vector v, call it v1, v2, how can we find a unit vector that points in that same direction? And the answer is, well, we get our vector v, we find out how long it is, and then we multiply it by 1 over the length of that vector, make that into a scalar, and we can do that. So such a unit vector would be 1 divided by the length of v, and that's a scalar, times vector v. And that is that.